So I actually hope that this is gonna be scary because I want it to be scary. And when you talk about Erlang or Elixir, one of the most interesting aspects and one of the things that is most often mentioned when it comes to whether you should use Erlang or Elixir is the distribution aspect and all the things that Erlang VM gives you when you want to create distributed applications. And when you look at the Elixir website, you can see that it uses the Erlang VM, which is known for running distributed applications. So you may assume that Erlang gives you an amazing tools that allow you to create distributed applications easily. But what does it actually mean? And what are the tools that Erlang gives you? And most importantly, what are the pitfalls and drawbacks that you should be aware of in order to be safe and be confident that your application works well. So starting with the basic, in order to have an Erlang or Elixir cluster, you have to have multiple nodes. And you start a node by running an IEX and passing name and cookie parameters, or by starting a release and providing these values in the VM args file. And then, if you have multiple nodes running in a network and these nodes can see each other, you can use node connect function, pass the node's name, and the runtime will take care of opening a TCP connection between the nodes. And via this single TCP connection, the nodes can communicate each other, they can send message to each other, and they also can monitor each other. So when you start an Erlang cluster, the nodes will take care of sending special heartbeat messages in order to let the other nodes know that they are alive. So this is all done through this single TCP connection. And the nice thing about Erlang and about distribution is the fact that Erlang clusters form a fully connected mesh. So when you add another node to a cluster and you call node connect, the runtime will automatically connect this node to all the nodes that are currently running in the system. And this is nice because it gives you the ability to communicate easily between each node, because every node sees all the other nodes in the system and can send messages to every node. But it also comes with a cost, because when your cluster grows and when you add new nodes, these connections there are more and more connections. And as I've said before, the Erlang uses heartbeat messages to monitor the nodes. So when you have a large number of connections, the number of the heartbeat messages is also very high. And what's more, the cost of connecting new node to a large cluster is also high. So this puts a limit on how much you can scale Erlang using the default distribution. And I think sources tell that the limit is about 50. So we are not talking about large global scale systems here. Like, we're not talking thousands of nodes. We're talking a few dozen of nodes. So we know that when you run an Erlang system, or Elixir system, you run multiple processes that are communicating through the network. And we also know that each process is uniquely identified by a PID. And the nice thing about PIDs is that they are unique across the entire cluster. So when we look at the PID, we can know for sure that this PID represents exactly one process in the entire cluster of nodes. And what's more, we can know which node the process is running on. Because the first value in the PID is actually the node identifier that is relative to the node that you are looking this on. So if there's a 0, it means that the process is local. And if the value is something else, it means that the process is running on some other node in the cluster. And the important thing is that this value is relative. So when you look at the same PID from different nodes, the value will be different because each node has a mapping from this value to the specific node address. So as I've said, 0 means local value. And When it comes to distributed computing, we have this notion of location transparency. And it means that if you have location transparency, you don't have to know the physical location of a process in order to send message to this process. And with PIDs, we have this. So if we are sending messages between the processes, the Erlang runtime will take care of checking where the process lives. And if the process is running on a local node, the message will be just copied to this process mailbox, as always. But if the process is running on remote node, the Erlang runtime will check which node the process is running on. It will take care of finding this node and choosing the correct node to send the message to. It will take care of serializing the message into a binary format. It will take care about sending this message through the network, through this single TCP connection that was formed when the nodes were connected. It will take care of deserializing the message on the other end and delivering the message to the destination process's mailbox. And it is amazing because in most of other languages, in most of other ecosystems, we would have to take care of all of this by ourselves. We would handle serialization, we will have to handle routing, and it's quite a simple task, but it can get messy, it can take some time, and we can make errors while dealing with that. And the Erlang ecosystem provides this by free, basically. And because we have this, because we can connect nodes together, and because we have location transparency, we can create distributed systems. And what you can often hear is that when you have a single node and you have processes running on this node and communicating through asynchronous message passing, it's quite easy to take these processes, add more nodes to the cluster, connect these nodes together, and it just works. Because since the processes were already communicating through message passing, the Erlang virtual machine will take care of all the rest and take care of communicating these processes between different nodes. So solved, right? Well, not exactly, because even though it looks the same when you send a message to a local and remote process, the behavior is completely different, and especially the guarantees are completely different. So let's talk about message passing, and especially about message guarantees. And let's imagine that we have three processes running on three different nodes. And we have process 1 sending messages 1, 2, and 3 to process 2. And we have process 3 that sends messages 4, 5, and 6. And let's assume that these messages are sent in the same exact order. So first messages 1, 2, and 3 are sent, and then process 3 sends message 4, 5, and 6. And the first thing you have to be aware of when creating distributed systems, that all messages can be lost. So Erlang doesn't guarantee you that the message will be delivered. And in fact, we call this semantics at most once. So it will be delivered either once or at all. It won't be duplicated, but you have no guarantees that it will be delivered. Another thing is the ordering of messages. So when you have two processes and they are sending messages to each other, the Erlang runtime guarantees that the ordering of this message will be preserved. So if the messages are sent in this order, so message 1, message 2, and message 3, then they will be delivered in this order, assuming that they will, because as I've said, all messages can be lost. So there cannot be a situation where message 1 arrives after message 3 because Erlang provides this ordering. But this is only true for a pair of processes. So when you have more than two processes sending messages, this ordering is not preserved. So the relative order of messages sent by processes 1 and 3 may be completely different. And why does it matter? Because we may imagine that we would be to write a simple presence mechanism, and we would like to know whether the user is online or not. So we could create a presence server running on some node or running on every node in that matter. And when the user logs in, a Phoenix process handling the connection will send a message to this process saying that user has logged in. And when the user logs out, the next message will be sent. But because we don't have this ordering between processes, between more than two processes, this message can arrive first. So if you have this logic that is basically a state machine that assumes that user logs in and only then he can log out, this logic of this state machine can be broken by delivering message out of order. And of course, when we consider sending messages through the network, we have to take care of delays. Because when you send a message to a local process, it's extremely cheap and extremely fast. It only requires copying the message to the process mailbox. But when you send a message to a remote process, you have to take care of all these steps. You have to remember that there is serialization, there is sending message through the network that may be slow. And there's also the fact that there's only a single TCP connection between the nodes. So when you send a large message or when you send many messages between the nodes, all the messages that have been sent after the large message can be delayed until this large message goes through the network. So now that we know how to send messages between processes and know what are the guarantees, we can wonder how we can actually know where to send message. Because even if we are running a single node, we often are not using PIDs. We are using names, which allow us to communicate with processes without knowing the PIDs. And the most basic tool when it comes to distribution is global. And global allows you to register process under any name, and it will be visible to all the nodes in the cluster. So you may have one global process that does something. You can register this process under a name and send messages to this process using this name. And how it works is that when you start a node, there's a special process called global name server. And it is started under the kernel supervision tree. So it is always started for you automatically. And it takes care of all the work that has to be done in order to register the process under a name. So when you want to register a name, a process that calls global register name sends a message to this global name server. And this server does something called distributed transaction. So it puts a lock on all of this process, making sure that only one process registers under the given name. So it's immediately visible that it can take some time, because when you have to coordinate multiple nodes and put a lock on all of these nodes, it can take some time. Then it sets up a monitor. So when the process that is registered goes down, or when the node that the process is running on goes down, this name is automatically deregistered on all the nodes. So we don't have to take care of monitoring the process ourselves, because the runtime and the global name server already takes care of that. And if all the steps succeed, we can return to the caller that it's OK and the process is registered. And then the nice thing is that this message is stored locally. So every node keeps an ETS table with all the names. So when you want to look up the name, you don't have to call any other node. You can do this locally, so it is fast. So it's all fine for now, but then bad things may happen, because the network can be partitioned. And when you have network partition and you want to register a process under some name, and you call global register name, the global name server will check all of the nodes that it knows of and tries to do this transaction thing. But since there is a network partition, this node A knows about no other node. So it assumes that it is alone and it is okay to register the process. But at the same time, the same thing can happen on node B. So on node B, P2 can also try to register itself as global. And now we have a situation where multiple processes are running at the same name and as one single resource. And in some situation, it may be okay. But when you, for example, want to have a global counter that sits on some process on some node, this situation where you have multiple processes running at this global, under this global name, it may produce different bugs that you should try to avoid. So what happens after this partition is healed? And the Erlang handles that by basically killing the node, one of the processes. And when you register the process under a name, you can specify the resolving function. But you have to remember that one of the processes that are conflicting will be killed and its state will be lost. So to sum up global, it's a global process registration that takes care of registering one process under some name. It favors availability. So if you have a network partition, you can always register a process, but it may result in inconsistent states in the cluster. And reading the information is fast, but saving the information is long and can be long because of the logs and because of the transaction. Then we can move on to process groups. So we have PG2 that takes care of creating groups of PIDs under some names. So we can create a group by calling pg2 create, and we pass a group name. And then we can try to add some processes to this group. So did I skip a slide? Yeah. So when you want to join a group, the pg2 module actually uses global. So it starts a global transaction, assuring that only one process at a time can add a PID to a group. It also uses monitors. So when the process or node goes down, it is automatically removed from the group. And it works. You can add another process, but again, you can have partition. So what happens during the partition is that because you have monitors, the nodes detect that the process is down and remove the process from the group. And you now have an inconsistent state in this process groups, because on the left side of the partition, the nodes see that in the group there's process P1. On the right side of the partition, we can see that in the group there's only P3. Of course, after some time, the network can heal and the nodes can be reconnected, and it will work again, and all the information will be merged. But for the time of the partition and some time after this, the state will be inconsistent. And this is quite important, because when you run Phoenix channels or when you run Phoenix presence, it actually uses PG2 under the hood. So every node is running a special PubSub process, and these processes are joined into a single group. And when you use channels to broadcast a message, this message is sent to this PubSub process. This process takes care of sending it to all the rest of the nodes, and the message is then broadcast from the PubSub process to the local processes. This is, of course, simplified because Presence uses a lot of optimization to make it fast, but that basically is how it works. And this means that when you have a partition, the nodes may lose some messages. So even though it's temporary, when you broadcast a message from node C or from any of node A or B, the message will not be seen by the nodes that are not connected to the cluster. So again, it will heal, but some messages may be lost. So if you are, for example, creating a chat system, or if you are relying on the information from Phoenix Presence, and you want to know whether the user is online or not, you have to remember that this information can be stale, messages can be lost, and you have to deal with that. For example, when you have a partition, you may see that the user is offline when it actually is online, but connected to a node on the other side of partition. You may also, because of the delays, see that user is online when he has disconnected already. And it should all be taken into account when you consider using some distribution from Erlang. So to sum up PG2, it handles process groups, so you can create a group of processes and do something with this group. It also favors availability. So when there's a network partition, you can add processes to a group. You can read this value, but you may read an inconsistent state. And as global, registration is quite slow because it uses distributed transactions, and reading is fast because the values and the PIDs are stored locally in the ETS table. So as you may see, both solutions that I presented are not consistent because they may lead to different views of the world on different sides of partitions. And it's actually true for most of the tools that you have in Erlang ecosystem, at least by default when you're not using any libraries. But you may need some tools that are strongly consistent because you may decide that it's not okay to have these different views of the world. So some solutions you may look at are I think the most known is consensus algorithm. And it includes Raft, Paxos, or Zookeeper Atomic Broadcast. And I know of implementations of Raft for sure, but I think that you can find something else. You may also look at distributed commits. So there's 2PC and 3PC. You may use quorums for reading and writing. But most of the time when you are using Erlang and you want a consistent view of the world, it's best to use just a single database. And I would recommend that if you are not sure, if you don't know better, just use a database and be sure that the view of the world is consistent. So I've been talking a bit about running Erlang in distributed mode and running cluster of nodes. But the truth is that all the things that I told you are actually also true for single node, because this is also a distributed system. We have processes that are communicating through message passing, and when you send a message, you have no idea if the message will be delivered, because even though the message is just copied to the mailbox, the process might die during sending this message. The destination process may also die and be restarted, but the message can be lost. The ordering can also be quite different. And when you look at the bigger perspective, you can also see that this too is a distributed system because you have different entities. You have mobile clients, you have web clients that are calling your API through the network. You have some databases that you deal with. And these databases can also be not consistent when you are using, for example, replication, or you are using database that is not consistent, like all the non-SQL stuff. you have all of this external API that you are dealing with. You have something to send emails. You have something to make payments and financial transaction. And all of this stuff is done through asynchronous message passing. And this means that messages can be lost, messages can be duplicated, messages can be reordered. And once you learn a bit about distributed systems and start to see the world as this scary place, you may try to find solutions that are capable of dealing with all these bad things that may happen. You start caring about idempotency, so you start to design your endpoints to be able to handle duplication of messages. You start to design your APIs and your processes to be able to withstand reordering of the messages. And you end up with a solution that is far more reliable and far more fault tolerant. Because web-based systems are essentially distributed systems. And when you learn to see it that way, you will end up with better solutions. So to sum up all of this and all of the stuff that you may hear about distributed systems, some say that distributed systems are magic because things are happening in all of the crazy way. But it's not exactly true because distributed systems are essentially about asynchronous message passing. And if you remember that, you are in the good position because then when you hear that some new fancy technology is solving all of the problems, you know that under the hood, there's messages. And there's only messages and failures, node failures, network failures. There's communication failures because messages are lost and reordered. And if you see that a solution tries to solve all of these problems and not telling you what are the trade-offs, you are starting to get suspicion. So if you know this stuff and you remember that all the fancy algorithms and solutions are just message passing, you start to see that it's all about trade-offs. And not only distributed systems are all about trade-offs, but all systems. So it's good to remember that all decisions have both advantages and disadvantages. And distributed systems are a cool way of learning that because these guys, I mean, most of the guys that are doing research in this area are really aware of all the trade-offs and all the cost that you have with every solution. And with that, I'm Maciej. I work at a company called Apionite in Poland. And thank you for listening.
Thank you. So we have quite a bit of time for questions. Very motivated Peter down there.
Hi. So you suggested global is a way for processes to find each other on different machines.
Yeah.
Because you can't have the PID to begin with. I was wondering if you knew how the global supervisor found the global supervisor on other nodes.
I know they listen for node up and node down messages that are sent by the kernel, I think. But I am not sure. I haven't read the global code. I just spent some time reading the Erlang docs. And this is what I got from these docs. But I am not 100% sure.
Sure, no worries. I'm now very curious. I'm going to have to look. Cheers.
Okay.
At the beginning, you sort of mentioned how there might be some problems in relation to, I think, noise or something. I'm not too sure, but you mentioned that like with Erlang, you get like minimum sort of like a maximum 50 nodes you'd recommend in a cluster. Can you go a bit deeper into why you believe that?
Yeah, so essentially, because you have this large number of connections, the cost of maintaining those connections is really high. When you have, basically, when you have n nodes, you have n squared connections. and it is really costly to handle all of those. So there is work to make Erlang clusters bigger, and the most successful one I know of is Partisan, and it is a library which replaces the Erlang distribution protocol. And instead of creating this fully connected mesh, it uses kind of a tree. And then you have small number of connections, but you don't have this ability to send a message directly to another node. Because if you have a tree, you have to go through multiple nodes to find the destination node. So it's a trade-off of whether you want to have many nodes or if you want to have a short path between any of the nodes. Thank you.
This may be a slightly newbie question, in which case apologies, but this sort of the ground layer, the first thing you covered is how the different Erlang processes get connected and set up this mesh network. And after that, we have global name service and everything is location transparent. I spend a lot of my time working with a containerized system where I don't really know where anything runs. So is there support in Erlang for bringing up that initial mesh, making the initial connection between the Erlang processes in that context?
Yeah, for example, you have this library called libcluster, and it gives you different strategies for connecting the nodes. And the most popular right now is when you run in Kubernetes. So the libcluster when started, the libcluster will call Kubernetes and get a list of addresses and automatically connect the nodes. So if you add another pod or when you deploy a new version, it will connect Kubernetes, ask for other addresses, and connect the nodes automatically.
Good. Anyone else? No? So I'll just double check the. Oh, yeah.
Thank you.
Definitely.